Dear students, in last class we have learnt design of a low pass filter. In this class we will take designing a Butterworth distal IIR high pass filter using bilinear transformation. Here the passband is from 0.7 pi to pi and the gain in passband varies from 0.6 to 1. Here the gains are in normalized values. The stop band is from 0 to 0.35 pi and the stop band gain should be less than or equal to 0.1. The sampling time is 0.1 second. Solution. We'll write here given specifications. Passband edge digital frequency omega p is 0.7 pi radians per sample. Stop band edge distal frequency omega s is 0.35 pi radians per sample. Gain in normal value at passband edge AP is equal to 0.6. Gain in normal value at stop band edge AS is equal to 0.1. Sampling time T is given as 0.1 second. These are specifications of high pass filter. To design any filter, we make use of analog low pass filter. So now we have to convert the specifications of high pass filter into low pass filter specifications. For that, what we have to do is we have to write the passband edge digital frequency omega p as stopband edge digital frequency omega s and vice versa. Converting high pass filter specifications to low pass filter specifications. Passband edge digital frequency omega p is equal to 0.35 pi radians per sample. Stopband edge digital frequency omega s is equal to 0.75 pi radian per sample. Gain in normal value at passband edge, it will remain same, that is AP equal to 0.6. Similarly, gain in normal value at stopband edge AS is equal to 0.1. AS is equal to 0.1. Now we will write the specifications of analog low pass filter. Gains of analog low pass filter will be same as that of gains of digital low pass filter, but the frequencies are to be transformed from the digital frequencies are to be transformed into analog frequencies by using bilinear transformation frequency relationships. So first we'll write about the gains here. gain in normal value at passband edge is equal to 0.6, and this is nothing but AP. Gain in normal value at stop band edge is equal to 0.1, and this is nothing but AS. Now we'll write analog frequencies. First one is passband edge analog frequency omega p equal to two by t into tan of digital frequency by 2, and that is 2 by 0.1 into tan of 0.35 pi by 2. I again advise you to convert this angle in radians into degrees. 12.256 radians per second. Unit of digital frequency is radians per sample. Unit of analog frequency is radian per second. Similarly, stop band edge analog frequency omega s is equal to 2 by t tan of digital frequency by 2, that is equal to 2 by 0.1 into tan of 0.7 pi by 2, that is equal to 39.2522 radian per second. Now, using the values of analog frequencies and the gains, we have to calculate order of Butterworth low pass filter. So right here, order of the filter. Remember all the steps in design procedure that I have dictated earlier, so that there will be no confusion when you start designing a filter. N1, if N1 is in fraction, then you have to round off that to next higher integer, that is positive integer. 1 by 2 log of 1 by as square minus 1 upon 1 by AP square minus 1 whole divided by log of omega s by omega p. That is equal to 1 by 2 log of one upon 0.1 square minus 1 by 1 by 0.6 square minus 1 whole divided by log of 39.2522 divided by 12.256, that is equal to 1.7267. This is not a whole number, so we have to round off this to next positive integer, and after rounding off we will call it as n. So n is equal to 2 now. So n is equal to 2 now. After finding n, in next step we have to find the normalized transfer function h of Sn. For even n, we know that h of Sn is equal to product of 1 upon Sn square plus bk into Sn plus 1 for k equal to 1 to n by 2, where bk is equal to 2 times sine of 2k minus 1 pi upon 2 times n. Since n is equal to 2, k is equal to 2 by 2, that is equal to 1, which means that there will be only one term in h of Sn. And bk is equal to 2 times sine of 2 into 1 minus 1 upon 2 into 2 into pi. That simplifies to 1.4142. Therefore, normalized transfer function h of Sn will become 1 upon Sn square plus 1.4142 Sn plus 1. From this normalized transfer function of low pass Butterworth filter, we have to obtain unnormalized transfer function h of S of high pass Butterworth analog filter. and that can be done by taking Sn value as omega c by s. Remember please, to convert h of Sn of low pass filter into h of s of high pass filter, we have to substitute for Sn equal to omega c by s. Now we have to calculate omega c. So write cutoff frequency omega c equal to omega s upon 1 by as square minus 1 raised to 1 upon 2n, that is equal to 39.2522 divided by 1 upon 0.1 whole square minus 1 raised to 1 upon 2 into 2. On simplification we get omega c as 12.4439 radians per second. Radians per second because omega c is analog frequency. Next we will write for unnormalized transfer function of high pass filter. To obtain unnormalized transfer function h of s of high pass filter from normalized transfer function of low pass filter, we have to substitute for Sn equal to omega c by s in h of Sn. That is h of s equal to 1 upon Sn square is omega c by s whole square plus 1.4142 omega c by s plus 1. Multiplying and dividing h of s by s square, we get s square upon omega c square plus 1.4142 into omega c into s plus s square. Substituting for omega c value at omega c is equal to 12.4439 radians per second, h of s will become s square upon 12.4439 square plus 1.4142 into 12.4439 into s plus s square. On simplifying this, we get s square divided by and changing the order of terms in denominator, s square plus 17.5982 s plus 154.8506. So this is unnormalized transfer function of high pass Butterworth analog filter. From this, now we have to obtain digital high pass Butterworth filters transfer function h of z. Now h of z is equal to h of s at s equal to two by t into the bracket 1 minus z raised to minus 1 upon 1 plus z raised to minus 1. So h of z is equal to 2 by 0.1 into 1 minus z raised to minus 1 upon 1 plus z raised to minus 1 whole square. Divided by 2 by 0.1 1 minus z raised to minus 1 upon 1 plus z raised to minus 1 whole square plus 17.5982 into 2 by 0.1 into 1 minus z raised to minus 1 upon 1 plus z raised to minus 1 plus 154.8506. Next, we have to take LCM and simplify. Four hundred into 1 minus z raised to minus 1 whole square divided by 1 plus z raised to minus 1 whole square upon 400 into 1 minus z raised to minus 1 whole square plus 17.5982 into 20 into 1 minus z raised to minus 1 into 1 plus z raised to minus 1 plus 154.8506 into 1 plus z raised to minus 1 whole square whole divided by 1 plus z raised to minus 1 whole square. Now 1 plus z raised to minus 1 whole square and 1 plus z raised to minus 1 whole square will cancel. Simplifying, we get h of z equal to 400 minus 800 z raised to minus 1 plus 400 z raised to minus 2 whole divided by 400 minus 800 z raised to minus 1 plus 400 z raised to minus 1 plus 351.964 into 1 square minus z raised to minus 2 plus 154.8506 plus 309.7012 into z raised to minus 1 plus 154.8506 z raised to minus 2. Further simplifying, we get 400 minus 800 z raised to minus 1 plus 400 z raised to minus 2 divided by, adding the like terms, 906.8146 minus 490.2988 z raised to minus 1. Please correct this as z raised to minus 2 plus 202.8866 z raised to minus 2. We have to write this h of z in standard form, that is constant term of denominator should be equal to 1. Therefore, we will divide both numerator and denominator by 906.8146 right here. $906.8146 by 906.8146. We get 0.4411 minus 0.8822 z raised to minus 1 plus 0.4411 z raised to minus 2 divided by 1 minus 0.5406 z raised to minus 1 plus 0.2237 z raised to minus 2. This is h of z. I request all of you to plot the frequency response of this high pass filter as we did it for the low pass filter in last question. Dear students, I'll stop the class here. Thank you.